This lesson is on basic antiderivatives, and so we've learned all of our derivative rules, and now basically we're going to take it backwards. The first thing is we've been approximating area using rectangles and trapezoids, and we were getting close to the exact area under a curve, but we didn't have the exact area. What we're getting ready to start allows us to find the exact area, and it's going to look like this. It's going to have a little curve here, an integrin, from A to B, and that's going to be like the x values you start and end at. F of x is the function, so the one that gives you the shape of the graph. Okay, and then the dx comes from basically that limit and the width of those rectangles going to 0, and I'll explain more about that in another lesson. But for right now, just understand that we can get the exact area using calculus, and it's called a definite integral. And we're going to start out with indefinite integrals, which do not have the a and the b, the starting and the ending points, and it does have a function in here. We're just going to be learning to go backwards from our derivative rules to get an original function, and we will put it all together in a later lesson. So let's start off with some examples here. And what I want you to do is think about what function would give you this as a derivative, okay? So not thinking about the sign and everything right now, it's just telling us to think kind of backwards. So what function would give you a derivative of 5? And hopefully you are able to think and say that that might be 5x. But that 5x would still have a derivative of 5 if it had any number added or subtracted onto it, because the derivative of a plane number is 0. So when we go backwards, we have to put plus c, and that stands for any number, positive, negative, whatever, that the derivative would be 0. So it could have been any version of 5x plus a number. Alright, now think about x cubed. Well, if you're going backwards, to take a derivative, you have to go down in power. So the original would have been x to the 4th. But you also multiply by that original power to the front and get the number in front. So here, what would I have multiplied 4 by so that I got a 1? And that would have to be 1/4. So you have to think backwards. Instead of multiplying, or you can think about multiplying the 4 times the 1/4 and getting the 1. But look at the relationship here. You had to add to get to the power when you go from this integral back to that original. And something happens with that front number. And we'll talk about that more in just a second. But anyway, again, this could have been any version of 1/4 x to the 4th with a number added on. So you always have to put a plus c. Okay, so now let's look at number 3. You try to think about number 3 and see if you can get the front number and the power right. So pause and do that. Okay, and hopefully you realized it would have been 1/3 x to the 6th, because if you multiply 6 times 1/3, you get 2, and if you subtract 1 from the power, you get the 5. Okay, so what have we done in these two? All right, you have worked backwards, which means in each case with the x, you added 1 to the power. So I'm going to say whatever that power was, we added 1 to that. And you actually, instead of multiplying with that front, when you go backwards, you divide. So you're dividing by 1 over whatever that power was. Okay, and then you always put a plus c. So this is kind of a generic rule for what's going on. And let's go to another example so you can kind of apply it. Okay, so here we have 7x squared. So by our rule, I'm going to add 1 to the power, make it a 3, and I'm going to divide by 3 in the front. So I get 7/3. Okay, put your plus c, don't forget it. If you have to think about it to check your work, remember just take the derivative. You would multiply by 3, which would just give you the 7 in front, and you would subtract 1 from the power, which would give you the 2. Okay, example 5. And if you want to pause and try it on your own, good time to do that. So example 3, you would add 1 to the power and get x to the 5th, and then divide by the 5 in front. So 4/5. So 4/5 x to the 5th plus c, again, because any number could have been added on. And again, if you want to check it by taking the derivative, you'll notice that you would get 4 in front, and the power would be 4. Alright, so that is your power rule in reverse. That's how the power rule works, but you know we had quite a few other rules. So let's look at a few other ones that will be kind of simple as well. Obviously, the derivative of e to the x is e to the x, so if I'm going backwards, the antiderivative is e to the x. But again, it could have added or subtracted any number, so you always have to put that plus c anytime you're going backwards. Now, for cosine and sine, you really have to think. The derivative of sine is cosine, and the derivative of cosine is negative sine. So when you're going backwards, what would give you a derivative of cosine? And that would be plain sine. How would I get a derivative of sine? The derivative of cosine is negative sine, and this is not negative. So what would make it give me a positive sine as a derivative? That would be a negative cosine. And again, put the plus c's with everything. So you just have to give a little thought sometimes. Alright, here's another one. What has a derivative of 1 over x? What gives you a derivative of 1 over x? That would be natural log of x. And when we go backwards, we need to put an absolute value, which I will explain again in a later lesson. A lot of it has to do with the fact that you can't take the natural log of a negative number, so we have to restrict ourselves to the positive there. But again, you want to put plus c. So that's one, again, that you'll make a change on. So 8, we had to think, hey, I've got that negative. 9, I've got to put that absolute value there when I go backwards. Alright, for 10, I wanted to show you that it's obviously power rule, but when you have plus between those things, it doesn't matter. Just do them both separately. So if I'm doing the antiderivative of 3x, I'm going to have x squared, and then a 3/2 in front. And then if I'm doing the x squared, I'm going to turn that into an x cubed with a 1/3 in front. But I still put a plus c on the end because any number could have been added or subtracted to that original function. Okay, just a couple more. So now, if you want to try the sine plus 3 cosine x, thinking about that one, you can pause. Okay, what would give us the antiderivative of sine? And that would be negative cosine, as we said before. And then the 3, when you have trig or e to the x, things like that, remember if it was multiplied, you just brought it down. So if it was brought down, I can just bring it back up one level. And the antiderivative of cosine is sine. So I just had to think through that one a little bit. Now 12 looks like it's way more complicated and it can't be done, but this is something that you can do a little bit of algebra on and come up with a polynomial. So you just have to use kind of power rules, or at least something similar that uses basic rules. So I'm going to multiply out the top, and see what I get. So that would give me x squared plus 2x plus 1 over x. And this is just my scratch work over here. So then I think about how can I rewrite that? Well, it's all over x, so I can put an x under each one and reduce. So I'm thinking x squared over x plus 2x over x plus 1 over x. And if I reduce, I get x plus 2 plus 1 over x. And I just rewrite my problem with that which is something that I know the rule for each thing. So the first one is going to become 1/2 x squared. The 2 is going to become 2x. And 1 over x is going to become the natural log of the absolute value of x. And again, I put my plus c at the end, but all this over here is my scratch work. And I do need to rewrite the problem using the proper notation. That's going to be important if you're doing something like this to make sure you get full credit. So basically today you're thinking backwards of these rules and seeing what you can come up with. And that concludes this lesson.